In this class, we are going to study specifically the equilibrium with 3 forces, 2 forces, and 4 forces. So first of all, when there are 2 forces on the object, what are the conditions for equilibrium? So the first heading is equilibrium with 2 forces. Force is a vector and it follows the rules of vector addition. So 2 forces can be cancelled out but with certain conditions. So 2 forces can be in equilibrium if 2 forces can be in 2 forces can be in equilibrium if the first thing is if they are acting on a single object. For 2 forces to be in equilibrium, they must be acting on a single object. 2 forces acting on 2 different objects can never be balanced. They can never cancel out each other. So for 2 forces to be in equilibrium, they must be acting on a single object. The second condition is they must be equal. They must be equal and opposite. So for 2 forces to be in equilibrium, they must be acting on a single object. They must be equal and opposite. And the last thing is they must be inline. Now, some questions related to the equilibrium of 2 forces. Question number 1. There are 2 forces which are acting on 2 objects. This is object 1, this is object 2, and here this force is F. Here this force is also F. So if we say, for example, if this force is 10 Newton and this force is also 10 Newton and we label them as F1 and F2, and a student states that F1 and F2 are balanced. If he says that F1 and F2 are balanced or in equilibrium, then point out the mistake in the student's sentence. Basically, the student is saying that the 2 forces which are shown, they are in equilibrium or they are balanced. Now you have to point out the mistake. Here the mistake is that these 2 forces cannot be balanced or in equilibrium because they are acting on 2 different objects. We'll write that although F1 and F2 although F1 and F2 are equal opposite and inline, although F1 and F2 are equal opposite and inline, yet yet they are unbalanced. The reason being, yet they are unbalanced as they are acting on two different objects. Since the two forces are acting on two different objects, although they are equal, opposite, and inline, yet they cannot be balanced because they are acting on two different objects. So this is about equilibrium of two forces. Now, if we discuss the equilibrium of three forces, equilibrium of three forces. So for equilibrium of three forces, the first condition specifically is for the net force to be zero, the three forces must make a closed triangle. So we must say that the three forces must make a closed triangle for the net force to be zero. So if we want the net force to be zero, then the three forces must be capable of making a closed triangle. For example, if you have three forces like this, F1, this is F2, and this is F3, you see they cannot make a closed triangle. So these three forces cannot be in equilibrium because your net force will not be zero. For the net force to be zero, the three forces must be capable of making a closed triangle. So if you get three forces like this is F1, this is F2, this is F3. One second. We have three forces, not four forces. For example, this is F1, and on the head of F1 we have F2, and on the head of F2 we have F3. So these three forces which are making a closed triangle, they can be these three forces can be balanced or in equilibrium. If you write they are in equilibrium, it would be wrong. There is a possibility of equilibrium because a closed triangle is formed and the net force would be zero. A closed triangle is formed and the net force would be zero. That's why the possibility of equilibrium is there. So we'll say that these three forces can be in equilibrium as they make as they make a close triangle, and the net force will be 0. This is according to the first condition of equilibrium. So first condition of equilibrium will be satisfied if the forces are capable of making a close triangle. So as long the forces are capable of making a closed triangle, there are chances that the net force would be 0. Now what about the second condition? To check the second condition, we have to see one thing. If the three forces are passing, or you may say intersecting, if the three forces are passing or intersecting through a common point, then they will be in equilibrium. So three forces will be in equilibrium if they are passing or intersecting through a common point. So if they are intersecting at a common point, then they will not generate any net moment. So basically, if you get three forces like this is force F1, for example, this is force F2, for example, and for example, this is force F3. These three forces can be in equilibrium because they are passing through a common point. However, if you take these three forces, this is F1, this is F2, and this is F3, they are not in equilibrium because they do not have common intersection. So here I will say that they have a common intersection. Whenever the forces have a common intersection, the second condition of equilibrium, the second condition of equilibrium satisfied. And when the forces do not have a common intersection, then we can say that it is no in the second case, you see there is no there is no common intersection. There is no common intersection. So second condition of equilibrium. So second condition of equilibrium not satisfied. So to satisfy the first condition of equilibrium, there should be a possibility of a closed triangle, and the second condition will be satisfied if the three forces have a common intersection. Let's observe some examples for that, and from examples we can make our conclusions and better understanding. For example, a classic example of equilibrium is balancing a ladder against a wall. So some questions are there about balancing a ladder against a wall, which explain the concept of equilibrium very well. So the question is, in which of the following cases, in which of the following cases the ladder is in equilibrium? So in it, which of the following cases the ladder is in equilibrium? The first case is number one. When you have a ladder and it is balanced again, it is balanced against, here you have the ladder, and this ladder is balanced against a smooth ground and a smooth wall. So here the ground is, for example, smooth. Smooth ground will not provide any friction. And here the wall is also smooth. Here the wall is also smooth. Now if we represent the forces at the ladder, then the forces on the ladder are the first case. The forces on the ladder are the weight of the ladder. Then we have normal contact force. However, friction is not present as the ground is smooth and wall is also smooth. So when we take a smooth wall and a smooth ground, the only force is the contact force. So weight of the ladder is acting in the center. And then we have F contact at point P, and same at Q we have another F contact. One thing is obvious, these three forces, if we join them with head to tail method, for example, if you add weight FQ, force at Q, and FP, they can never make a closed triangle. It's not possible. So first condition of equilibrium is unsatisfied because the given forces are unable to make a closed triangle. So we'll say that equilibrium not possible. Need to write equilibrium not possible equilibrium is not possible as the equilibrium is not possible as the forces are unable to make a close triangle. So whenever the forces are unable to make a close triangle, the equilibrium is not possible. Here, what is the problem? The first condition or the second condition? When a triangle is not formed, the first condition is unsatisfied. So in the given example, we must say that the first condition of equilibrium will check the second condition if the first condition is satisfied. So the first condition of equilibrium is not satisfied. Even the forces cannot be balanced. So for the forces to be balanced, the forces must make a closed triangle. If a closed triangle is not formed, then the forces are not balanced and the first condition is unsatisfied. So number 2. In the second example, let's take a ladder which is balanced against rough wall. The wall is rough. Every surface provides a contact force irrespective of whether it is smooth or it is rough. So every rough or smooth surface provides a contact force. However, the smooth surfaces do not provide friction, while the rough surfaces provide the friction. And the net force is the sum of the friction and the contact force provided by a surface. So contact force is always perpendicular to the surface. This is the rule. So we have rough wall here, and even the ground is also rough. So a ladder is balanced against a rough wall and a rough ground. Now if we keep a ladder here, if we keep a ladder here, this ladder will have some forces. First of all, on the rough ground, we have two forces. Whenever you get a rough surface, on the rough surface, if the surface is rough, then two forces would be there. If tendency to slide is towards right, if the object is allowed to move or it is pushed and tendency to move or slide is towards right, if tendency to move is towards right, then obviously friction will be towards left. So friction is against the tendency to slide, and the contact force is always, so if tendency to move is towards right, then friction is towards left, and F contact is always perpendicular to the surface. As a result, the net force of these two will be here, and this force is the net force. Now, the wall is rough and the ground is also rough. So as a result, If we focus just on point P, the two forces will be the first force that we'll get is the contact force. Now just think about that. If this ladder falls, then point P will slide downwards or it will slide upwards. If you look carefully, the point P will slide downwards. If some point has a tendency to slide downwards, then friction on that point is upwards. So point P has a tendency to slide downwards. So friction on point P will be upwards. However, force on P, which is net of these two forces, friction and contact force, that should be drawn like this. The net of the friction and the contact force is the force at P, and that would be Fp. So Fp is the force on P, that is the net of the friction and the contact force. Now this was point P. Now just think about point Q. Point Q. For point Q, the tendency of Q to slide is towards right. Q may slide towards right, and the forces on Q will be, if Q is sliding towards right, then friction on Q will be towards left. So friction on Q will appear towards left because Q has a tendency to slide towards right. So this is the friction on Q, and the normal contact force on Q and the normal contact force on Q is perpendicular to the surface. So the resultant of these two forces will be, the resultant of friction and F contact will be force on Q. So this is the net force on Q, and this is the net force on P. So net force on Q and net force on P are shown, and the third force here is weight. Now let's think, what is the possibility of equilibrium? Is equilibrium possible or it's not possible? So if we draw the resultant forces, because F contact and friction are the individual forces, however, we will focus on the net force at P, net force at Q, and net force that is weight ka force. So basically, if we focus on this ladder, which is kept on the rough wall, and the ground is also rough. So it is rough wall and the ground is also rough. So when the wall and the ground both are rough, then the situation is that then the forces on the ladder are, you need to draw the net force and not the individual forces. So if this is the ladder, so this point is point P, and this is point Q. So point Q was, the net force at Q was here. So this is FQ. FP would be, so this is FQ and FP, and the weight of the ladder is, if you see, it will act at the central point. So this is the weight of the ladder. Now let's check whether or not the forces are in equilibrium. So to check that, first of all, let's draw the closed triangle. If the closed triangle is formed, then the first condition is satisfied, yet they are not in equilibrium, then we will check for the second condition. So let's check for first condition and second condition. We have to see whether the equilibrium is there. So So equilibrium, for equilibrium, the forces must make a closed triangle. Let's check whether they make a closed triangle or they are not making a closed triangle. So first of all, if we draw a force that is mg, mg is vertically downwards. mg is vertically downwards. If we draw the other forces like force at, this is mg, and if we draw a force at q, for example, so this is force at q, and force at p would be obviously, so this is force at, so mg, then you have force at q, and then you have force at p, then you have force at point p. And what do you think? A closed triangle formed or it is not formed? It is formed. The possibility is that it will be formed. So it's possible. While while the common intersection point, just for example, if the if the forces are capable of passing through the common intersection, extend them and observe whether the intersection is common or it's not. So if a closed triangle is formed and the intersection is common, then the relationship is equilibrium, then the given situation is equilibrium, then the conditions are met. The first condition and the second condition both are satisfied. What is the first condition? The net force must be zero. That is shown by adding, that is shown by drawing a closed triangle of vectors. Since we get a closed triangle with, so whenever the closed triangle is formed, then it is the first condition which is satisfied, and if the second condition is satisfied, then if the second condition is also satisfied, then the equilibrium will be achieved. However, the first condition and the second condition, they are independent of each other. According to the first condition, the three forces must make a closed triangle. According to the second condition, the three forces must pass through the common intersection. If they are passing through the common intersection, then we'll say that the three forces so the three forces, our conclusion would be the three forces. While writing an answer of this part of the questions, you have to write possibilities, not as a fact. We'll say three forces. If you write are in equilibrium, it would be wrong. You have to write three forces. So the three forces cannot be in three forces cannot, here they are in equilibrium. The three forces can be in equilibrium. Can be in equilibrium. The three forces can be in equilibrium as they can make a closed triangle So the three forces can be in equilibrium as they can make a closed triangle and they have a common intersection. So whenever the three forces acting on an object are passing through a common intersection and they are capable of making a closed triangle, the possibility is that the object may make a closed, then the object can be in equilibrium. So for equilibrium, the conditions are that the forces should be passing through the common intersection. The forces should be passing through the So for the equilibrium of three forces, they must make a closed triangle and they must have a common intersection. Another case,